Take a few minutes here to look at the routing table. The routing table components. The objective for this module is 3.2. Interpret the components of the routing table: prefix, network mask, next hop, routing protocol code, administrative distance, metric, and then gateway of last resort. So a topology table, a routing table, we've looked at a little earlier. In this one we have a couple of different, actually 3 different routing protocols here. The R is going to be RIP, C directly connected, which is really not a protocol. The L is the local, and you notice that the locals have a 32-bit mask, and that's what the forward slashes are in these things, what our prefix is. And this one /24, which is going to be the 255, 255, 2550. Same here, 192, 168, it's a 30-bit, which is going to be 255, 255, 255, 252. It actually is going to be used to break the network, subnet the networks that go between routers, because we only need 2 addresses to go from one router to the other. So instead of using an entire Class C network, we subnetted so that we only have 2 usable addresses. We have 2 usable addresses, a broadcast address and a network address on those. And then the L's, you notice, have a 32-bit mask, which says that it is a host address. More connected here, this one, 192, 168, 3 network, which is going to be, where are we? One of these is going to be the entire network that's connected to it. Looks like it's the only one I didn't. No, here we go. 3 network, which is going to be this entire Class C network that's attached to this router here. So looking at these things, the C directly connected, L local, O is OSPF, D is going to be EIGRP. We'll look at those abbreviations again in a minute. And then C is directly connected, R is RIP. The primary protocols that we use today are OSPF and EIGRP. The reason EIGRP is D is for dual, which is the algorithm that it uses in order to do the calculations. RIP is an objective, if you recall, for ICND1, and we will configure a RIP router a little bit later. We can go through that process. The routing table, we need to know how to interpret which protocols are used, and I kind of tend to always get ahead of myself. The table has directly connected networks, statically configured routes, and as well as dynamic routes. So in this thing, multiple routers to advertise on this one. When we do that, the edge router here, when we connect these things together, the edge router can have a static route because there's only one place to go. It can have a default route, and that's going to be the only static route that it needs. It can only go one place, and that's to this next router. Same could be said of this guy. It only goes to one destination. We have multiple networks connected to it, so it is going to advertise multiple networks. I know how to get to these 3 directly connected, but going out, it could have a well, actually, it could have a would not be good. Would have a dynamic. Could have a static route. It could have a static route, a default route, because that's for outgoing. Everybody else would either have to have a protocol here, a dynamic routing protocol, or have individual entries for each of these networks on every router in order to get it there if we're going to do a static route. So a dynamic route is more practical when we get into the other things. We still have to eventually tell the world about our routes, our networks, and how to get to them. Stumbled through that one, huh? So I do, and this is a, you know, that's kind of ugly sometimes because my tongue gets tripped up. But directly connected, the C's and the L's here. The C directly connected, and that's typically going to be the network. The L is going to be the IP address of the connected interface. Route source is where the route was learned. The destination network is the remote network, and the outgoing interface is the exit interface down here at the bottom. So the route source where it's learned here, C and L, and we have the others. We have the R for RIP, the O for OSPF, and the D for EIGRP. The destination network, in this case, we're doing the directly connected ones, 192.168.2, and then the outgoing interface, serial 030. And if we look up at the table, the route source, 192.168.2, we have the C and the L here, the 30-bit mask and the 32-bit mask directly connected, and it goes out serial 030. So these are going to be directly connected. They're directly connected. These are actually, we would presume, since it's the 30-bit mask, that these are the interfaces that connect routers together, because there are so few addresses that are available there. If I can get back. The source letters, we've said it a couple of times. R is RIP, Routing Internet Protocol. C, directly connected. O is OSPF. D is EIGRP. And then a static down here, S with a star is going to be a static. The star makes it the default route. The default route, gateway of last resort, is 192.168.2.2. Which is this one down here, to network 0.0.0. No other routes to send here. This is every network, because if we have an unknown and we have a gateway of last resort or a default route, then we send it to that interface. And the way we write this one is just an IP route is the way we write a static. So it's IP route 0.0.0.0 with a 0.0.0.0 subnet mask, and then whatever the next hop is to configure a default route, a static route. Any static route, the command is going to be IP route, and then whatever the default route happens to be. One of the easier ones to write. Remote networks here. These are remote networks. Remote source identifies how the route was learned. And in this case down here, the remote source, O, is going to be OSPF. The destination network identifies the address of the remote network. So we're trying to get to 192.168.4 network. The administrative distance, we're going to have a table here in just a second, is how trusted is that source. And each of them, OSPF, happens to have an administrative distance of 110. So it's going to be more trusted than some and less trusted than others. And again, we're going to have in a few, we're going to have a couple of slides where we'll have the table that shows the administrative distance for each of the routing protocols. Identifies the trustworthiness of the route. How trusted is it? The metric identifies the value, is basically how much it costs, for lack of better terms, to the remote network. The lower values indicate the preferred route. So in this case, the lower the cost, just like if you're going to buy a product, the lower the price, the better. Next hop is the IPv4 address of the next router. So this is going to be the IP address of the interface that is directly connected. The route timestamp, when the route was last heard, the last time, so this one's 16 minutes and 40 seconds ago was the last time that we knew that it was valid. We don't know that it's invalid because we haven't gotten any notification to say that it's no longer any good. The outgoing interface identifies the exit interface, the outgoing interface, the interface on the device where the route table is that it's going to go out of. So the remote networks, the components of the route entry. The prefix length, shorthand way to express the subnet mask, sometimes called CIDR, classless internet domain routing. And what it basically is how many ones are in the subnet mask. So 192.168.2.2/24 instead of 192.168.2.2.255.255.255.0. Would be nice if we could actually use these configurations this way to write addresses, network addresses in the Cisco configuration. You can do that with IPv6 but not IPv4. So how much of the network address? This one would be a /8, /16, /24 would be the prefix length of the CIDR notation for each of those. Talked about, we said we would get to the administrative distance defines reliability. How trusted is the network? And I don't know if they're smart or dumb, but when we look at the directly connected, it has an administrative distance of 0. You can't get any better. The lower the better. Lower is better in administrative distance. So a directly connected route is the most trusted. How can we mess that up? It's directly connected. We put in the IP address and the router says, yep, I know about this guy. Static, and this is the one whether it's smart or not, static route, one that we type in, hopefully don't make any typos, is going to have an administrative distance of 1. The only thing that is more trusted than a static route is directly connected. Internal EIGRP, and because internal there is also an external EIGRP, but internal EIGRP, which is a Cisco proprietary, which they have shared with everybody, but it's still a Cisco, is 90, and it is the most trusted of the dynamic routing protocols. OSPF, Open Shortest Path First, which is as a standard that we would use, has an administrative distance of 110. And then RIP is 120. External EIGRP 170, unknown 255. They're only locally significant. They're not transmitted. So if we have different protocols on different routers, we could have different administrative distances. And again, the lower the better. How trusted is the route? And what actually will happen if we have RIP and an OSPF and an EIGRP protocols all running and all advertising the same routes, the only one that we'll see in the route table is going to be the EIGRP. If we do a static, it's going to be the one that's going to show in the route table. So they're in the forward base, they're there on the router, but only the most trusted one is displayed in the route table, because remember, it's the thing that you used to determine where we're going to go. The metric in each of the routing protocols has a different metric. The values associated with specific routes, ranked from most to least preferred. So the lower the cost, and cost is one of the specifics. It's not cost for all of them. RIP, for instance, hop count. EIGRP is a composite. OSPF is cost, as we can see down here. But the lower is better, because it's going to be each of them, although the actual cost is only using one protocol. If we had 3 hops versus 1 hop, yeah, we can say that would be the 1 hop would be the better way to go. Going to cost us less in resource to get us there. The best path or the lowest metric in the routing table, best path, lowest metric in the routing table, and multiple paths with equal costs are load balanced, equal load balancing. And then this one, the best path with the lowest metric in the routing table, and also with the lowest administrative distance. It's going to use the best of everything. So we use the lowest administrative distance and the lowest metric as the preferred route. So with that, what we talked about was the routing table, the components of the routing table, local networks, the ones that are directly connected, the gateway of last resort, also called the default route, remote networks, how we get that information. We had different protocols, the route components, We talked about the protocol codes, prefix length, and administrative distance. Administrative distance is how trustworthy is the route, is the protocol, and the metric is how the routing protocols determine which of the available paths to take if there is more path available. So we're going to quit with that one. The next one is going to be how the table is populated by the different routing information sources. Hope to see you there.